We are jumping straight into an expert analysis of patent application US 2026/0138640A1 titled Vision-Based System Training with Simulated Content. This document tackles one of the most massive bottlenecks in autonomous driving, the sheer scale of data required. Instead of relying purely on cars driving millions of physical miles just hoping to encounter every single bizarre driving scenario out there, this architecture uses simulated content to exponentially blow up the size of training data sets for neural networks. We are going to break down the exact mechanisms they use to turn standard, everyday video data into infinitely variable training environments. So here's the core mechanism. The patent proposes supplementing physical sensor data with highly engineered simulated datasets to radically accelerate neural network training. Think about it. Vision-only vehicles need millions upon millions of examples just to learn how to identify objects and accurately judge distances. By taking real-world video and intertwining it with procedurally generated simulations, the system essentially creates the exact training sets the algorithm is missing. It completely bypasses the need to go out and physically record complex, dangerous driving events.
Section 1. The limitations of purely visual systems.
Purely visual systems operate entirely without radar or LiDAR. Now, that's great for keeping costs down, but it introduces some massive data acquisition challenges. The hardware baseline here relies solely on a suite of cameras: front-facing lenses at node 202, pillar cameras at 204, bumper cameras at 206, and rear cameras at 208. These lenses literally act as the eyes of the vehicle. And because there's absolutely no supplementary detection hardware involved, this captured physical video serves as the rigid, unbending starting point before any sort of simulation can even happen.
But here's the catch. Relying entirely on that physical camera suite creates a critical bottleneck. Collecting physical data for every single extreme weather condition or rare hazard is just mathematically and financially unscalable for a global fleet. I mean, if an algorithm needs thousands of examples of a car navigating heavy snow, while a pedestrian simultaneously crosses against the light, while waiting for a fleet to organically stumble upon that exact chaotic scenario is incredibly inefficient. On top of that, purely visual baseline systems can really struggle in fog, snow, or heavy rain. That means the baseline data collected in those conditions is often just too poor to be useful for initial training. For a self-driving car to be truly safe for everyday consumers, it desperately needs a workaround. Section 2. Simulated Training Architecture. To fix that massive data bottleneck, engineers designed an architecture that shifts the burden of edge case generation off physical roads and straight into data centers. The topology relies on three core pillars. First, you have the fleet of vision-only vehicles at node 102 capturing the raw data. Then, there's a central network at node 110 handling these vast streams of information. And finally, there's the simulated content system at node 120. The vehicles supply the real-world foundation, the network processes it all, and the simulated system modifies it. Component 120 is the true engine of this entire patent. The simulated content system is defined as a network service that receives vision-based data and transforms it into content models. Essentially, this system takes a brief, standard clip of a real-world drive and prepares it for synthetic, procedural manipulation. It doesn't just awkwardly slap a digital image on top of a video, it structurally dissects that real-world clip so it can be used as a flexible, malleable core for endless simulated variations.
Section 3. Data Processing and Annotation.
Moving from physical capture to synthetic generation takes some really rigorous technical processing. The data lifecycle operates in this continuous, closed loop. First, the vision collection happens right at the vehicle, gets transmitted to the network, and the ground truth labels are extracted. Next, over in the simulation generation flow, targeted scenario variables are selected and the actual synthetic training data is generated. It's a constant stream of information being filtered, processed, and routed straight into the simulation engine. This entire workflow operates in a very precise four-step sequence. Step 1 is the raw capture on the vehicle itself. Step 2 is processing the ground truth labels, which basically means identifying where the road is, where the cars are, and where pedestrians are standing. Step 3 is generating the simulated model, and finally, Step 4 is associating specific index attributes with it so the machine learning algorithms can actually retrieve it and learn from it effectively later on.
Crucially, all this processing relies on a strict hierarchy. Priority 1, the absolute highest priority, is always assigned to road edges. Why? Well, because road edges are the foundational anchor for the entire simulated environment. Before you can even think about simulating a synthetic car or crazy weather event, the system has to flawlessly understand the physical boundaries of the drivable space. Only after that's locked in does it move down to priority 2, which includes lane lines, static signs, and dynamic moving objects.
Section 4. Generation of simulated scenarios.
Once the base data is highly structured, the system starts computationally injecting synthetic variables. It's a fascinating contrast. You have the original video providing the base ground truth, literal road edges, and static geometry. Then the simulation system introduces profound variations, sometimes completely swapping out the template. For instance, it can take a mundane urban intersection captured by a car, synthetically transform all those buildings into a quiet suburban environment, and then insert a dynamic hazard, like a synthetic child running out into the street. It completely alters the context of the original data.
The software routine dictates exactly how this generation occurs, specifically starting over at block 500. By obtaining the collected target vision information, the system programmatically identifies specific model attributes from those processed ground truth labels we talked about. This is the underlying logic where a standard, boring, sunny day driving clip is computationally dismantled, appended with complex new attributes, and then reassembled into a novel, highly complex simulated model.
The sheer number of specific parameters the simulated content service can alter is virtually limitless. The system can change color attributes to test if the algorithm struggles with, say, dark vehicles against dark backgrounds. It can alter object types, modify the acceleration vectors of surrounding synthetic traffic, introduce harsh weather conditions, or massively scale up the density of vehicle traffic. By manipulating these variables, it perfectly emulates scenarios that would be way too dangerous or statistically just too rare to ever safely capture physically on public roads.
Section 5. Closing the training loop.
Generating all this synthetic, variable-rich data is just the first phase. The system still has to seamlessly feed it back into the neural networks. The final routine executes this exact transmission. It pulls the specific simulation variables required for the current training batch, generates the final dataset, and transmits it directly back to the machine learning algorithms. This effectively updates the vehicle's driving logic without the physical car ever having to experience that specific hazard in real life. It's incredibly efficient.
The patent concludes with a highly definitive claim. It states that this architecture generates significant benefit and increased performance of the machine-learned algorithms that can be continuously optimized based on any number of criteria. What they are outlining here is a continuous, highly efficient optimization loop. Traditional methodologies require fleets to physically drive millions of miles just hoping to stumble upon edge cases. This system replaces that slow physical grind with instantaneous, infinite computational generation. It's a massive paradigm shift.
This detailed architecture brings up a really provocative technical question regarding the future of autonomous engineering. As the fidelity of these simulated content systems advances to perfectly mirror reality, to the point where artificial rain, lighting, and erratic synthetic pedestrians are literally indistinguishable from real-world sensor data, will physical edge case data collection become entirely obsolete? Because if neural networks can be trained flawlessly in a data center using dynamic simulations based on foundational ground truth labels, the physical limits of autonomous vehicle training might have just been permanently bypassed. Something to think about.